So we're going to be looking at analyzing rational functions of any form. Just take that stuff from yesterday, the AH and K stuff, and just shelve it. I'm talking here about any rational function. A rational function that looks like this, for example. Which cannot be arrived at by transforming 1 over x, and it cannot be arrived at by transforming 1 over x squared. Those ones we looked at yesterday were just kind of an introduction to rational functions. I think mainly so you can learn about asymptotes and all that other stuff. But this is a rational function that you cannot get from yesterday's work. So we're going to be analyzing those rational functions. Now it turns out that when you have a non-permissible value, and I hope everybody would see that this rational function I've made up has 2 non-permissible values of x. X cannot equal plus or minus root 3 because if it does, the denominator will be 0. Well, it turns out that at x equals non-permissible values, when you look at the graph, the evidence of the non-permissible value might look like one thing, or it might look like a different thing. There's 2 different ways a non-permissible value can manifest itself to you on a graph, can show you or reveal itself. And one is called a point of discontinuity, and the other one has to do with an asymptote. And we'll get to that. The one thing, the third bullet here, is not in your textbook, and I don't understand this. It's in the curriculum, it always has been in the curriculum, and when the authors wrote the textbook, they never addressed it. So this is an important idea, even though you're not going to see a lot of questions with regards to it. You should be able to look, for example, at this function here, and at the end of this lesson, tell me where the horizontal asymptote is going to be. Horizontal. So whether it's at y equals -1 or 2 or 5 or 4 or whatever, there will be a horizontal asymptote here. Not all rational functions have horizontal asymptotes, though. Okay, so let's get started. 2 types of non-permissible values. So I have a function, and I redesigned this lesson and most of this unit. So please, if you see that something I have up here is different than what's in your handout, you need to let me know. But I think these, I double-checked, and sometimes I need to triple-check, but I double-checked. So the non-permissible value of x in f of x is what? This is not a trick question. What value of x are you not allowed to use in that function? 2. You know, we could say the non-permissible value is 2. We can say the domain is x is not allowed to be 2. I want to avoid that confusion and just have you write the number 2 in there. 2 is not allowed. Is everybody clear on why? Because the denominator is x minus 2. You can't divide by 0. Similarly, this also has a non-permissible value of 2. And remember, my introduction to this was me telling you that non-permissible values in terms of a graph show themselves in different ways. There's 2 different ways they can reveal themselves. And we're going to learn about that right now. We're going to use a graphing calculator to graph each of these functions, one at a time, and talk about the non-permissible value. So I'm going to start off with, I actually want to start off with g of x. Let's graph g of x on our calculator first. So what are we going to put in? We do need a set of brackets around the numerator and around the denominator. Let's go zoom 6. And throughout this learning phase of what's going on, I may be kind of guiding you along the way to tell you to use particular zoom settings or window settings. But we're going to start off with zoom 6. Make sure I've entered it correctly. We're looking at g of x, which is the bottom function on the screen. Looks okay, so zoom 6. Well, isn't that weird? It's a line, but it's not a line. Okay, and I want you to think carefully about this, because a line is an infinite number of points. This is straight, but it's not a line because x cannot equal 2. Let me demonstrate something to you. If I set up my table and I start at 0 and go up by 1, and I go into my table, I get an error at 2. If I don't want to do that, maybe I can quit out of here. I can go trace and enter 2. No, I'm going to go trace and enter 1. Oh, it tells me that when x is 1 on this function, y is 0. I'm going to go trace 3. When x is 3, y is 2. I'm going to go trace 1.999. It tells me the y coordinate when x is 1.999 is 0.999. But if I go trace 2, there's nothing there. And this is the difficult thing to wrap your head around. There's what we call a hole, which is what your textbook refers to it as. I think we can elevate our language to a better level here and say it's a point of discontinuity. But the size of it is infinitely small. I can put into this function, g of x, which is at the bottom of the screen, I can put into g of x for x any number as close to 2 as I can conceivably imagine, and I'm able to calculate a y coordinate. But I can't put in 2. If you want, this is interesting, don't worry about why your calculator is programmed this way, but if you go zoom decimal, very often you can see the hole. Now, how big is the hole or point of discontinuity? Infinitely small, but we draw it as if it's an actual break in the graph that's big. So when we sketch this function for g of x, we can get a little more detail to it if we want. You can see that the y-intercept is -1, the x-intercept is +1. You're going to get a line that looks like this, except over here at 2, and just wait for the whole thing so you can see what's happening here. There we go. That's what you get. So we have a point of discontinuity. This point of discontinuity is at 2. And you want to be very careful. Is that point a point on the function? No. So when I write the coordinates of this point, this is going to sound weird, I'm writing the coordinates of a point that isn't there. What's the y coordinate of the point that's not there? Well, if we go here and we look at trace 1.9, we get a y coordinate of 0.9. If I go trace 1.95, I'm getting a y coordinate that's closer and closer and closer to 1. And we could try it from the other side as well. I could go trace 2.01, and you get a number very close to 1. So what's happening is as x is getting closer, and this will be important in a minute, as x is getting closer to the value that it's not allowed to be, 2, y is getting closer to the value that it is not allowed to be, which is 1. So this is at 2, 1. There will be a way for us to determine the y coordinate without using a graphing calculator. Now, what about the other function? I'm starting off with the one with the point of discontinuity, even though it's new, because it's easier to graph. Okay? It's easier for you to draw. This next one is not quite, it's a little messy. So this time what we have is x squared minus 8x plus 15 divided by x minus 2. Now there is still a non-permissible value of 2. the graph cannot exist at x equals 2. I'm on a different zoom setting. I want to go back to zoom standard, zoom 6. And this is an interesting one as well. So I'm going to, as I said, I'm going to guide you with some window settings here. I'm going to change the window settings to start at -5. And for y, I'm going to go down to -12 and up to only, say, 8. It doesn't really matter. I'm just giving us the opportunity to get a better visual of what the graph looks like. So I'm going from -5 to 5 and -12 to 8. And I might tweak that a little bit in a second, but I think that'll be sufficient to make my point. So this is what we are looking at. And I want to now just try trace 2 again. Nothing, right? Which makes sense because the graph can't exist at 2. But what happens if I go trace 1.5? Well, I get a y coordinate of -10.5. What if I go trace 1.8, which is close to 2, but it's not 2, so it's still allowed. I get a y coordinate of -19-ish. If I go trace 1.99, my y coordinate starts exploding in the opposite direction. It's becoming -300 and something. If I go trace 1.99999, I don't want to break the calculator. I think it can handle this. I'm getting -300,004. And I think you can understand that this graph is going down forever. But since it can't equal 2, there must be a vertical asymptote there. Similarly, on the other side, if I go trace 2.0001, which is really close to 2, I get a very large number. And what I am demonstrating to you, and it's really the only important thing about this warm-up, is that at x equals 2, there will be a vertical asymptote. So we have a point of discontinuity here. And as much as I say, oh, we should use point of discontinuity, I will very often refer to it as a hole. And over here, we have a vertical asymptote. I have chosen this example for f of x mainly for my calculus students, the students that are going to take calculus later. And I'm not going to do a perfect job of graphing this. But if you're interested, it turns out that this also has a slant asymptote. Whoops. A slant asymptote about like that. This is not important for Math 30. I'm just pointing out that this function comes down and then up, whoops, and then up along here, getting closer. Horrible. Comes down and up, getting closer, and here it's the same thing. So not only is there a vertical asymptote, there's a slant asymptote, which you do not need to know how to calculate in this course. Okay? Let me highlight for you the difference between these two functions in terms of important ideas. Just locked up my computer, so the important ideas are about the point of discontinuity. For the function on the left, it results Did it come up? I think it might have. There we go. This is the important aspect of the graph on the left. This is the important aspect of the graph on the right. That's my point. When I say a non-permissible value can do one of two things, it's these two things, vertical asymptote or hole. Now, how is it we determine which it is? Well, Let's simplify each function. So we're going to transport ourselves back in time to Math 20, where we have a rational expression. You know, in Math 20, you may not have called it f of x, but you would have had a rational expression. And the first thing you learn in that unit is how to simplify rational expressions. What is the one thing you always want to do with anything that's a rational expression? Factor completely. So let's factor. Does this factor, are there two numbers that multiply to give 15 and add to give 8? Negative 8, sure. Negative 3 and negative 5. So it factors into x minus 3, x minus 5. And in the denominator, it's x minus 2. Okay, so we've factored everything, but nothing cancels here. In other words, this function was already simplified. Well, I don't even want to put it that way. If I said simplify that function, you don't have to do anything. What about this one? For g of x. G of x is going to be equal to the top factors into x minus 1, x minus 2, over x minus 2. And you're taught that the purpose of factoring is because factors are things you cancel. I mean, even going back to junior high or elementary school, if you had a fraction of 12 over 42 and you reduce that down to 6 over 21 and you reduce it further down to 2 over 7, I think that's right, isn't it? The reason that's working is because you're saying in 12 and in 42, each of them has a factor of 2, so I can cancel it. And then in the 6 and in the 21, each of them has a factor of 3, so I can cancel it. That's what's happening when you're canceling. So we can do this. So g of x is equal to x minus 1. By the way, throughout this lesson, if you happen to see something that's highlighted, that's because I highlighted it to fix something in my note package that I've already done, but you might want to note that it talks about part D in your handout. It should say part C. So, are you with me? Okay. There is a glaring error on the board, and I'm not just talking about, it's a little error. It's huge. There is a mistake on the board. It's intentional this time. What's wrong with what I've written? Craig? Right. If I say g of x is x minus 1, are you allowed to put 2 in here for x? Sure. But the function has a non-permissible value. So you need to add that non-permissible value statement. Now, you don't need to over here, but it's not wrong to. You don't need to because it still has that factor in the denominator. So if I could somehow graph the line x minus 1, well, let me graph x minus 1. I'm going to go back and graph x minus 1. And you're going to use your memory to remind yourself that this is what the function g of x looked like, except there was a hole, right? So x minus 1 is not correct. X minus 1 with the condition that x can't equal 2 is correct. So what are we learning from this? If a factor that has a non-permissible value cancels, it will produce a point of discontinuity. If it doesn't, it will produce a vertical asymptote. That's the lesson to be learned here. Gustav, are you with us? Okay. So, denominator factor cancels. Sometimes it's just easier to write whole. Denominator factor doesn't cancel. vertical asymptote. And I want to address now g of x again. Do you agree that the whole or the point of discontinuity for g of x was this? So this is hard to put into words, but I'm going to do my best. What this means is that this is not a point on the function because it's the coordinates of the whole. So x is a value, 2 is a value of x that's not allowed, right? You're not allowed to use x equals 2. And you're not allowed to get y equals 1. But guess what happens if you take the x coordinate that you're not allowed to use and put it down here into the simplified form? You get the y coordinate that you're not allowed to use. So if you ever want to find the y coordinate of a whole or a point of discontinuity, you simplify it and then you put the number in, even though you're not allowed to. Because what you're doing is you're using the value of x that's not allowed to get a value of y that's not allowed. It's kind of weird. All right. So describe the behavior of the graph near the non-permissible value. I've already explained this to you visually with the graph and the trace function. On f of x, as x gets closer to that non-permissible value, what does y do? Let me put it back up here, but I may need a little bit of help here. It was x squared minus 3 x plus 15 minus 5x plus 15. Minus 8x, thank you. Plus 15 divided by x minus 2. Am I correct now? Okay. So I'm just going to go zoom 6. I know I changed the window settings, but it doesn't matter. What we're talking about here when I write this statement that you can see to the left of the calculator is as I go trace equals 1.9 and trace 1.99, what's happening to the function? And the answer is the function is exploding to either positive or negative infinity, depending on which side you're on. And that's the definition of a vertical asymptote. And by the way, you can have a rational function where on both sides it explodes to positive infinity. On both sides it explodes to negative, or it can be like that, or it doesn't have to be plus and minus. Whereas here, as x approaches 2, what does the function approach? It approaches the number 1. That's the point, no pun intended, is that there's a hole or a point of discontinuity at that location that as x gets closer to being there, y zeroes in, gets closer to a particular number. All right. Write each rational expression in factored form and tell me about the non-permissible values. That's what I'm asking. I'm not asking about domain, range, any of that stuff. We're focusing on non-permissible values. So in order for you to ever tell me about a rational function where it's just a polynomial over a polynomial, can you double check to make sure f of x and g of x are written the same in your handout? While we're at it, h of x and k of x. Okay. Before you can tell me anything about a rational function, before you can analyze, look at the title of this file, Analyzing Rational Functions, everything needs to be factored. I can't factor x squared plus 4. Now I have a question for you. On the top, I have a factor of x And on the bottom, I have a factor of x squared plus 4. And on the top, I also have a factor of x plus 2. Is there a common factor I can cancel? No, nothing cancels. Are there non-permissible values for x? Change your mind?
Yes.
There are none, because to find non-permissible values, what you're doing is you're saying, what happens if I solve this non-equation, right? This is the only way I can get a non-permissible value is through division by 0. And when you try to solve this, you don't get a solution because I think most of you can see this, but just taking it one step further, you get that statement. It's a dead end. So what do we conclude about this function with regards to non-permissible values? There aren't any. There are no vertical asymptotes. There are no points of discontinuity. In other words, there are 0 breaks in this function. It exists everywhere continuously from negative infinity to infinity. And later on, if you want to graph these, you can. Over here, g of x, and we might graph them if we have time. But as I said, I've redesigned this unit, and I've redesigned this lesson in particular. I think we're okay for time, but I don't want to get off track. I can factor an x out of the numerator, and the denominator is a difference of squares. So first of all, by factoring everything completely, it reveals the non-permissible values of x. Remember, with a rational expression, you eyeball the denominator, because if the denominator is 0, that's not allowed because you can't divide by 0. So if x plus 2 is 0, that would make x negative 2, so x can't be negative 2. If x minus 2 is 0, that would make x 2, but x can't be 2 because then x minus 2 would be 0. So these are non-permissible. However, those cancel. And what we're left with here, and I suspect maybe you have a little bit more room to write than I do. Not much, I guess. What we're left with is this statement that g of x is equal to x over x minus 2, but we need to say x is not allowed to be that negative 2, even though the x plus 2 went away. And you know what? I would just put all the non-permissible values. You don't need to, like between you and I shouldn't need to tell you that x can't be 2, because you see an x minus 2 there. But why not put it anyway? Now, what does that mean? It means that the surviving factor is going to produce a vertical asymptote. So we're going to have a vertical asymptote at x equals 2. This is the vertical asymptote. We are going to have a hole or a point of discontinuity at negative 2 comma something. At negative 2 comma what? We could put this original function into a graphing calculator and start going trace negative 2.001 and seeing what it's getting close to. Or we can remember what I've told you. If you want to find the value of y that's not allowed, take the value of x that's not allowed and put it into this function. So g of negative 2, looking here, is negative 2 over negative 2 minus 2, which I think is 1/2. Negative 2 over negative 4. So again, what we're doing is we're saying you can't use negative 2 because negative 2 doesn't exist for x, but let's use it to find out the value of y that doesn't exist. Any questions with f of x or g of x? Okay, x squared plus 2x over x minus 4. Okay, well, we have a vertical asymptote at x equals 4. Because this is telling us x cannot equal 4, and because the x minus 4 survives. Do you get what I mean by survives? It doesn't cancel? Any questions with h of x? Okay, let's factor k of x. And you know, admittedly, everybody, these functions I'm giving us for this first example are not complicated. You know, the factoring can get more complicated. Right now, I just want you to focus on getting used to what the non-permissible values turn into graphically. So when you look at this function, it's pretty clear that x is not allowed to be negative 2. Will that reveal itself as a vertical asymptote, Declan, or as a point of discontinuity?
Point of discontinuity.
And how do you know that? Like, what do you...
Because the factor in the denominator cancels.
Right, because the factor in the denominator cancels. So as soon as you see that that cancels, you know that there's going to be a point of discontinuity. This time I will write the word whole. It will be at negative 2, comma, some y coordinate that doesn't exist. So don't forget, this is not a point on the graph. It's a point that's not on the graph. If we simplify this, we get k of x equals x. But of course, y equals x is a line that contains every point, every point. We want a line that doesn't contain this point, so we have to say x is not allowed to be negative 2. Christian, how are we going to find the y coordinate of the whole? Right. We take the non-permissible value for x, and we use it to find the non-permissible value for y. But I can't put that x equals negative 2, or x is not allowed to be negative 2 up here, because then I'll be dividing by 0, but I can put it in here and write k of the x coordinate that doesn't exist will give me the y coordinate, which is x, which is negative 2. So in other words, we feed the non-permissible value of x into the function to get the not allowable value of y. Any questions with any of those 4 functions or the basic idea here? All right. So we would like to match these functions, and you know, one of these functions happens to be one that we just looked at. It doesn't matter. Let's take a minute, everybody, please, and factor all of these completely. point here, everybody, is not to know exactly what this graph of each of these three functions looks like in excruciating detail. The thing is to look at function A and recognize there are two non-permissible values for A, but at the non-permissible value of -2, there will be a hole or a point of discontinuity. So we're looking for a graph that has a hole at -2 and a vertical asymptote at +2. Well, that's that one. Right? So when we look at these two non-permissible values for A of x, the x plus 2 cancels. The non-permissible value that goes with the x plus 2 is -2, but that means that's the x-coordinate of the hole because this is the rule. When they cancel, you get a hole. You with me on A of x being graph 2? Okay. You know, you have to look at the big picture here, and if I were to look at B of x, I wouldn't have even bothered factoring anything because the denominator contains a single factor. It's a binomial and it's quadratic, but it has no zeros. There's no value of x that makes x squared plus 1 0. What does that mean? I'm looking for a graph that's continuous everywhere. Well, this is what it happens to look like, strangely enough. It's a weird graph. So this must be B of x, and by process of elimination, C of x must be the first graph, and that certainly makes sense because C of x has two non-permissible values. Neither one of the factors that create them cancel, and that means they're both vertical asymptotes at negative and +2. And again, you don't have to worry about why the shapes look like what they look like. That's for later. Any questions with example 2? We have one more example related to this where I teach you one extra layer and then there's one more thing we have to look at. So you're given a rational function and you're asked to find the equation of it. So what we're going to do is we're going to build this equation from the ground up. We're going to say that looking at the graph, I see a vertical asymptote at x equals 2, which means there has to be a factor of x minus 2 in the denominator. I look at the graph and I see over at -2, there's a hole or a point of discontinuity, which means there is also, I want to be clear here. We have two non-permissible values. So if x can't be 2, then we have to have x minus 2 in the denominator. If x can't be -2, we have to have x plus 2 in the denominator. But since there's a hole at -2, I need that in the numerator. Are you with me on the equation building so far? Okay, but here's the thing. This can't be it because you're told it's quadratic in the numerator. And I will show something to you. If you thought that was the function, can everybody agree that x minus 2, x plus 2 is x squared minus 4? It will just make it easier for me to enter it into the calculator. So let me graph x plus 2 divided by x squared minus 4, which is what we have written so far. And this is what it looks like, but that is nothing like what that graph looks like. Does this graph on the calculator have a vertical asymptote at 2? Yes. Does it have a hole at -2? Yep. Zoom decimal very often reveals the whole. But it's just wrong, isn't it? So there's one other thing that we need to look at. And it's the new thing I'm telling you. There is an x-intercept at 7. Now think about what this means. It means that if x is 7, y is 0. Let me repeat that. If x is 7, you have to get 0 for the whole thing. That means we need something on the top to make that happen, and it's going to be x minus 7. That's the only way with all of these factors, with the function written in factored form, this is the only way you're going to get 0 for the whole thing by putting 7 in for x. So let's add that to what I have on the calculator and confirm that it works. So I'm going to go insert and put in another factor of x minus 7. I guess I'll go zoom 6 just to bring it. Looks good. Oh, we're not done. We have to expand this out to get the A, B, C information. So f of x is x squared minus 5x plus 14 minus 14 over x squared minus 4. I'm assuming you can FOIL out x minus 7, x plus 2. Are we in agreement with that? Okay. That makes A 5, B 14, and C 4. So you would enter 5, 1, 4, 4. And anytime you get a blank that is 2 digits, you would use 2 digits on the answer sheet. So any questions with number 3? Factor in the denominator that doesn't cancel, vertical asymptote. Factor in the numerator that doesn't cancel, x-intercept. Factor in both, whole. But there's one more piece of the puzzle, and it's horizontal asymptotes. So why do we get a horizontal asymptote? Let me sketch a graph for you. There's a horizontal asymptote, and I just sketch a graph, and the graph maybe looks like this. The first thing you need to get over is this. Horizontal asymptotes can be crossed by the function. And it's because functions are allowed to go up and down that happens. Vertical asymptotes are not allowed to be crossed because graphs of functions can't go back and forth. Okay? So don't worry about the fact that it intersects in places. What is important here is that I'll put a number on here for you. Let's put 10. As x takes off to infinity, y gets closer to 10. What a horizontal asymptote is what y is getting closer to when you go to extreme values of x. You with me? If you look at a vertical asymptote, as x gets closer to that number, y takes off to infinity. But with a horizontal, as x takes off to infinity, y approaches a number. It's backwards. So let's see if we can figure out what the asymptotes of these 3 functions are. My tabs got all screwed up here. Give me a second. How can I fix that? Let's do... So, for each of the following, determine if there is a horizontal asymptote. We're going to do this on our graphing calculator. So you're going to enter this in for y. X squared plus 2x minus 24 divided by brackets 2x minus 5. And by the way, horizontal asymptotes have nothing to do with factored forms. In fact, we would prefer it to be in this form. And I'm going to go zoom 6. I better double check. Nope. I'm going to go zoom 6. And I'm going to make a general observation that this graph, I will show this to you in pieces. In this location, this keeps going up. I mean, could there be an asymptote over here someplace that this is curving against? Maybe. I think the only way for us to decide is to start looking at larger values of x. Let's go to our table and let's scroll to larger values of x. Well, y just keeps getting bigger. Maybe it's going to settle down around 100, maybe. So I can set up my table to start at 0 and go up by 100 and go to my table. And it appears as though y just keeps getting larger. Now, one thing. In this course, if there's a horizontal asymptote on this side of the graph, it will be on this side. You will never have two horizontal asymptotes. We will see that in calculus. So I don't need to look at negative infinity. What I can say, what I can conclude here is there is no horizontal asymptote. What about the next one? So we have 3x minus 10 divided by 2x squared in brackets plus 35. Well, I'll go zoom 6 again. It sure looks like the x-axis is an asymptote. Let me adjust things for you to show you it in a little more detail. I'm going to change the window settings to go from -2 to 2 for y. Going to adjust it even more. It's asymptotic there. The x-axis is an asymptote, so we can write y equals 0 is the equation of the asymptote. And finally, 5x squared minus 2x minus 9 over 2x squared minus x minus 10. Go zoom 6 again, just to start off there. This is not, everybody, how you are going to be finding horizontal asymptotes. Would you agree there appears to be some horizontal asymptote there? If I want to find out what it is, I can go to my table. I'm going to start at 0 and go up by 1. And I'm going to take a peek in my table. And as x gets bigger, y gets smaller and smaller. I'm going to ask a question. I don't know if you understand this or if it makes sense to you, but do you agree as I scroll to larger values of x, y is getting smaller, but it's getting smaller by a smaller amount each time. It's slowing down. You could sit here all day and scroll down, and you would discover that even at some point it might say 2.5 in your table, it will be a number bigger than 2.5. So y equals 2.5. And now I'm going to explain to you the rules, which are at the bottom of your page. If the degree of the polynomial in the numerator is bigger than the degree in the denominator, you will not have an asymptote. And I want to explain why. I think you can understand why. It doesn't have to be memorization. If you have a degree 2 polynomial over a degree 1 polynomial, do you agree with this idea? At incredibly large values of x, it's going to be the higher degree terms that tell you the overall value. At x equals 10 million, do we really care about this minus 24? No. And at x equals 10 million, we don't even care about the 2x. We care about the x squared. So at incredibly large values of x, on the top, these two things might not even be there. It might as well not be there. And on the bottom, this 5 might as well not even be there. And what you end up with is x over 2. One of the x's cancels. So it's just going to keep getting bigger and bigger. As x gets bigger, the whole thing's going to get bigger. If it's opposite, then y equals 0 is the asymptote. And I'm going to use a slightly different reasoning. Do you agree that since the top is linear and the bottom is quadratic, the bottom grows quicker? At infinity, the bottom is going to be growing infinitely larger than the top, so the whole thing collapses to 0. And if the degrees are the same, all you have to do is divide the coefficients of the highest degree terms. 5 over 2 will give you 2.5. Bigger degree on the top, the thing just keeps going up. Smaller degree on the top, it's going to come to 0. Equal degrees, divide the coefficients. So between that and these ideas, that's how you analyze rational functions. Factors in the denominator produce non-permissible values. If you can cancel a factor, there will be a hole in the graph. If you want to find the y coordinate of the hole, put in the non-permissible value of x anyway into whatever is left. And if the factor does not cancel, then you get a vertical asymptote, and x-intercepts are represented by lone factors in the numerator. And then know how to find horizontal asymptotes. So, not a lot of questions here. With this unit, I've taken a different philosophy. I want us to focus on what is important. Not a lot of questions. You need to know all of those things we learned today.